Modeling the effect of wind seems to be pretty straightforward. It looks as though we simply have to push the fire through the forest with a certain velocity. If the left curve is the temperature distribution at time 0, after one time step, h, it will be shifted to the right curve, and the amount of shift amounts to the time step times the velocity. As we are storing these values in an array, couldn't we simply shift their position in the array? The tricky thing, however, is that the time step times the velocity is really small. We would have to shift these entries by a fraction of a step. How would you do that? Here comes a different approach. I want to get the new value, the value on the right curve, at the position x0. I get that new value by looking it up on the original curve, step size times velocity to the left from here. And now the trick is to use the derivative of this function. Let's write down what this new value is. The new value after one step, time equals the time step, h, at this position, x0, is approximately the old value, t of 0, x0. And now we have to take care of the difference between these two. And we estimate it using the derivative. So our correction, the length of that green line, will be step size times velocity, this length, times the derivative, the slope of our tangent. The derivative is the partial derivative of temperature with respect to x at time 0 and position x0. And we have to be a bit careful about the sign. If the derivative is negative, such as in this case, we have to go up, which means we need a minus sign in front. So that's the trick. We use the spatial derivative to accomplish this shift. As usual, however, as with all these methods, we have to be careful about not taking too large steps. This value, the step size in time times the velocity, has to be reasonably small. In particular, it should be pretty much smaller than our grid size, delta x. The way to compute this derivative is, of course, to use a central difference formula.